Okay. We just started with specific heat capacity in the last class. So I'm going to start off from there. What is the definition of specific capacity, anybody?
The amount of energy required to increase the temperature of 1 kilogram of substance by 1 degree Celsius or 1 Kelvin.
Right. The amount, and which one has, so the amount of energy required to increase the temperature of 1 kilogram of any substance by 1 degree Celsius or 1 Kelvin. That is called specific heat capacity by definition. And which substance has the highest specific capacity? Water. Water has the highest specific capacity in the universe, basically. And some others are actually kind of close to it. Ice is almost half of that of water. Common metals, such as copper. Copper is 390. I think I gave you some numbers, right? Copper is 390. Aluminum is around 900. Mercury is around 138 or something like that. So compared to all that, water has got the highest specific capacity, and that's the reason why water is used in the radiator of your car, because it can go in and then collect all the heat and come out. All right? So we saw the equation Q equal to mc delta T, which is actually the amount of energy involved. So Q is equal to mc delta T. You can use this equation to find the quantity of heat energy or energy required. So if I have the mass, I have the specific capacity, and I have the change in temperature, I can just plug it in and get the answer for the amount of energy. And I think I went on to discuss about calories and stuff like that. Did I explain about calories?
I don't think we did.
Okay. So if you have to find out how much energy is needed to maybe make a cup of coffee, all right? So let's say if mass is 200 grams, which is 0.200 kilograms. Specific capacity of water is 4,186 joule per kilogram Kelvin. And the temperature change the water is going to go through. Right now, the temperature of the water is like 24 degrees Celsius. So if it is going from 24 degrees Celsius to 100 degrees Celsius, what is delta T? How much is delta T? It is 76 degrees Celsius or 76 degrees Kelvin. Same thing. Now plug it in and find out Q. Q is equal to mc delta T. This is how you find the amount of energy involved. So 0.2, somebody does the calculations, times 4,186 times 76. Tell me what the answer comes out here. This is the amount of energy needed to make a cup of coffee. What do you have? $63,627. Okay, 630 joules. This is the amount of energy that is needed to make a cup of coffee. Okay? Now, joule is not a unit that you're familiar with. We are familiar with calories. So the connection to calories is this. 1 calorie is 4.186 joules. The calorie is actually equal to 4.186 joules. So how many calories is this? Go ahead. 63,630 joules is how many calories?
15,200.
15,200 calories are required in order to make a cup of coffee. Is that clear?
Yeah. Got it.
Now, in comparison to this, let's look at how many calories in a cookie.
300.
Let's say a small cookie. So, how many calories in a cookie? 200?
Shit.
Is that right?
Oh my.
I don't think so.
That is the right
I don't know
answer.
about that one, G. I
The
don't
number
think
of calories in a cookie is actually 200,000 calories.
So the line was
So the amount of energy needed to make a cup of coffee is 15,200 calories, and the amount of energy required, that you get by munching on one cookie is 200,000 calories.
Damn.
Now,
I wonder how much
this
you
is
think
the
they
actual scientific calorie. This is so. What happened is when you throw these numbers on a label, do you think anyone will actually take it if you tell them it is 200,000? So that's why they started shortening it, and they started writing 200 kilocalorie. Even then, they were not able to fool the public because it says kilocalorie. And then they said, oh, let's define a new kind of calorie called food calorie. And they started defining one food calorie is equal to 1 kilocalorie. And therefore, they changed this to 200 calories.
Shit.
They just basically knocked out the K from there. Because if you ask them, what kind of calorie is it? Oh, it's a food calorie. This is a scientific calorie. What's the difference? Hardly any difference. That is how we are getting fooled. So what is being put on the label is actually the food calorie, 200 food calories, which in fact is 200,000 scientific calories. So do you get the connection there? So how many food calories is this? How many food calories is this? 15.2 food calories. So the amount of energy needed to make one cup of coffee, all that energy required to kind of boil the water and all these things is 15.2 food calories. Whereas what you get from one cookie is 200 calories. You get it? So if you're going to stand on a treadmill and then run on the treadmill and let the treadmill churn the water and create the water's temperature to go up, all right, so that you can make this happen, you will need to burn this much food calorie. You get it? But one cookie will get you that. So it's easy to dump in the calories. So yeah, just have some information about the calories part of it. The scientific calorie, food calorie, they're all different. Joules is the SI unit of energy. All right? Now let's look at some situations here. We'll use the entire board and therefore make provision for taking notes properly. So suppose I take ice at negative 20 degrees Celsius. Ice is at negative 20 degrees Celsius. And if I heat the ice at negative 20 degrees Celsius, and suppose I supply some energy to this ice at negative 20 degrees Celsius, what happens as you heat this ice? What will happen?
It melts.
It melts?
Temperature goes down.
Temperature goes down when you heat it?
No.
Temperature goes up.
The temperature goes up.
Temperature goes up. Ice is not going to melt until it reaches the melting point. So when you supply heat to this ice at negative 20, it will change from ice at negative 20 to ice at 0 degrees Celsius. So ice is basically warming up. Ice will never melt. And for this process, we use the equation Q is equal to mc delta T. Q is equal to mc delta T to find how much energy is required for this to happen. What is M standing for? Mass of ice. What is C standing for? Specific capacity of ice, which is like 2090. 2090 is the specific capacity of ice. And delta T is how much here? 20. So if you plug all that stuff, we will be able to find out how much energy is going on. Now, the energy that is in a body, what is it called? Another name for it, symbolized by the letter U. Internal energy. And what is internal energy made up of? What is internal energy made up of? This table has internal energy. What is it made up of? What kind of energy? Particles, kinetic energy, and potential energy. The particles have kinetic energy and potential energy. And the sum of these two is what makes up the so-called internal energy. Do you understand this? Yes. We are talking about the internal energy, which is sum of the kinetic and potential. What is the definition of temperature? Temperature.
It is proportional to the average kinetic energy.
It is proportional to the average kinetic energy of the particles, right? Yes?
Yeah.
So if temperature is rising, that means the average kinetic energy is going up. Make sense?
Yeah.
Is the temperature rising here?
Yeah.
That means the average kinetic energy is going up. So basically what's happening is, it's still ice. Ice at negative 20, ice at 0. What is different with this ice here is that it has got more kinetic energy. Is that clear?
Yeah.
Because its temperature is higher. But the potential energy is not going to be affected. The particles are still almost the same spaced. So potential energy is hardly affected, but kinetic energy has increased. Now what happens if I still supply heat?
They keep increasing.
What will happen to the temperature of ice
Rises.
when it starts melting?
Decrease. Stays the same.
It's a tricky question.
Nothing.
What will happen to the temperature of ice when it starts melting?
Stays the same.
Stays the same. Stays the same. Ice temperature will not change unless it is completely transformed into water. So when you start seeing ice melting, the temperature is still 0. So what is happening here is that when you start heating ice at 0, it changes ultimately to water at 0 degrees Celsius. See, temperature has not changed. Temperature has not changed. But the phase has changed. The phase is going from a solid phase to liquid phase. Alright, so solid phase is moving on to liquid phase when ice at 0 is melting to become water at 0. Is that clear?
Yes, sir.
So there's a phase change, but there's no temperature change. Since there's no temperature change, what form of energy has actually changed? Is it the kinetic or the potential? It's a potential. Because you see, in ice, the atoms are bound to their neighbors, but when it melts, the bonding is broken, and therefore the potential energy is increased. So whatever energy is put into the ice at 0 is actually used to break those bonds, and that is why this has more potential energy, but the kinetic energy is exactly the same. The temperature has not changed. Okay, tell me. Ice at 0, water at 0. Which one has more energy?
They're the same.
Water at 0 has more energy.
Yeah.
Stand up.
I just said that internal energy is made up of kinetic energy and potential energy. The kinetic energy has not changed, but the potential energy has increased. So this water here has higher amount of energy. And
Yes.
that is not visible. You'll have to go that way. Somehow make your way that way.
Okay. Can you go back with?
Yeah, why don't you just create a gap over there? Can you go to your right?
Henry, you sit right here.
Yeah.
All right. This has more energy compared to ice at 0. But stick a thermometer in here and here, the thermometer will get fooled because the temperature is still the same. And because this has more energy than this, we call that energy hidden heat,
Hidden heat.
which is the same as latent heat. Another word for hidden is latent, which is actually meaning hidden heat. Yeah.
So if ice or water is if it's the same temperature, how is it different? Like
Because it's got more potential energy.
but like how could let's say you have ice at 0 degrees Celsius, how does that turn into water? At
You're
zero,
supplying-
at 0 degrees
you're
Celsius.
supplying heat.
Then how is the water the same temperature as the ice?
See, internal energy is made up of kinetic energy and potential energy, correct?
Yeah.
This internal energy is the same kinetic energy, but a larger potential energy. So it's got more energy there than here.
So that's a change in
But
phase.
this is what will reflect on the temperature. So
That's
temperature.
the measure of it.
You understand?
Yeah.
Kinetic energy is a measure of temperature. Kinetic energy is a measure of temperature. And that's why temperature reaches 0, 0, but there is some hidden amount of energy sitting here. And that hidden amount of energy is called latent heat. It's called latent heat. And how we calculate the amount of energy required is by using a different formula, and that formula is Q equal to mL. And what is L standing for? L stands for specific latent heat. Now write down the definition of specific latent heat. It is the energy needed to change the state of 1 kilogram of a substance at a constant temperature. It is the amount of energy needed to change the state of 1 kilogram of a substance at a constant temperature. So, to change the state of 1 kilogram, it is L. To change the state of 2 kilograms, it will be?
2L.
To change the state of 3 kilograms?
3L.
To change the state of m kilograms?
ML.
That is how this equation is. Right? Now, so Q equal to ml is the amount of energy needed. So you can see there's no delta T here because there's no change of state, change of temperature. What will happen if I continue to heat this? It will increase in temperature to a maximum of 100 degrees Celsius. By the way, this process of going from here to here is melting. Right? So, this is the melting point, and it is melting. That is basically the term that is used when something goes from solid phase to a liquid phase. So, when it is going from here to here, the temperature is changing. So, which energy form is changing? Kinetic or potential? Kinetic. You got it. So, kinetic energy is changing, but potential energy kind of stays the same. And the amount of energy needed for that is given by the same equation, Q equal to mc delta T. What does M stand for? Mass of water. What does C stand for?
Specific heat.
Of water. You see, it was ice here. Now we're using the specific capacity of water, which is 4,186. And delta T is how much here?
Change in
Which is 100. Right? You see 100 right there. So this is the equation that is used. Now what will happen if you still supply heat to water at 100? It already reaches maximum. What will happen?
water vapors.
It changes into a gas. So therefore it goes from here to steam at 100 degrees Celsius. So until all this water is changed to steam, the temperature will stay the same. And so this is going from a liquid phase to gas. What do you call that process? Vaporization. That's called vaporization. Now there's a difference between vaporization and evaporation. Can you tell me the difference?
No.
Evaporation and vaporization. Do you know what they are?
Evaporation continues.
Hmm?
Evaporation continues.
Evaporation continues.
Wait, did you say what's the difference between evaporation and evaporation?
Vaporization and evaporation.
Evaporation's like clouds in the water, right?
Yeah.
Yeah? Like with the water, you put water in a cup and it
Like this.
evaporates.
This water is now evaporating.
Yeah.
Yeah. that's true.
Evaporation,
Yeah, but what is vaporization then?
liquid to gas.
Isn't that the same thing here? Evaporation is also liquid to gas.
Same thing.
Evaporation is going out into the air. Vaporization is just going
Mm,
everywhere.
into the air and
It's
everywhere.
the same thing. It's a trick question. It's the same thing.
No, it's not the same thing.
It's gotta be.
All right, the answer is this. Vaporization takes place at a constant temperature, such as boiling point.
Oh.
When something is boiling, vaporization is what the term is used. Like you're at the boiling point. If it is changing from liquid to a gas, that is called vaporization.
That's what
But if something is changing from liquid to gas at any temperature, that's called evaporation. So right now, this water in the cup is actually evaporating. What is evaporation? Escape of the most energetic molecules from the liquid out of the liquid.
Oh.
That is evaporation. It's a slow process. Evaporation is a very slow process, tiny process. But vaporization is a very quick process.
Oh my.
All right, so what is vaporization? Vaporization is something that takes place at a fixed temperature, which is the boiling point of a liquid. And it is a fast process. And evaporation, on the other hand, can take place at any temperature. It can take place even at 0 degrees Celsius. Evaporation can take place at any temperature. Okay? And it is a slow process. Evaporation is a very slow process. Okay, so you got that?
Yes, sir.
Vaporization, liquid to a gas phase. So what kind of energy is increasing here? Kinetic or potential? It is potential. Kinetic is not changing because
Oh.
temperature is not changing. Therefore, kinetic energy is not changing. But the potential energy is changing. Why? Because the molecules are going to be removed from the liquid and it is pushing the atmosphere and moving out. So it's a lot of energy required there to get out. And that is why the potential energy is changing. All right. So the amount of energy needed for this is given by the equation Q equal to ml. Once again, this is also latent heat. Which one has more energy? Which will burn you more? Water, boiling water, or steam at 100 degrees Celsius? Steam at 100 degrees Celsius can burn you more because it has more internal energy. Or in other words, latent heat. It's got hidden heat. So if steam comes and falls on your hand, it will surrender its latent heat and then become boiling water. So the first bundle of energy it will give you is a big packet of energy, big bundle of energy. That's why this will burn you more. All right, so what will happen if I keep heating?
Nothing.
What will happen to steam?
Goes away.
What goes away? Steam can increase in temperature to 150 or 200 or 300. You can actually get superheated steam. You can actually push the temperature of steam to really high temperatures.
That hurts.
Hmm?
That hurts pretty
Oh,
bad.
that's more, of course. So this has got more energy than here. So you can have steam. Steam is not always 100 degrees Celsius as people normally think. You can actually superheat steam to higher temperatures. So inside a pressure cooker, the steam inside the pressure cooker is not at 100, it's higher. So the steam coming out from a pressure cooker actually has got more energy than a common steam, right? So the equation that you're going to use over here is Q equal to mc delta T again. M stands for the mass of steam that is being converted. What does C stand for?
Specific capacity
Of steam. Specific capacity of steam, which is like 2010. specific capacity of steam is like 2010, this is 4186, and this is 2090. You see?
Yeah.
And why the specific capacity is different is because of the way the atoms are arranged in these kind of things. Now let's talk about the reverse process.
No.
Reverse process. If I steal energy from this, it'll cool down to become 100 degrees Celsius steam, right?
Yeah.
If I steal energy from here, what will happen?
Turn into water.
It'll turn into boiling water. And this process going from here to here is called condensation. Condensation, going backward. So for example, if you're trying to cook something and the water is boiling, you put a lid on top. When you put a lid on top, what happens to the steam? The steam at 100 is going to come to the top and touch the lid.
Start dripping.
It starts dripping, right? So when the steam comes and touches the lid, it surrenders its latent heat to the lid, which is cooler. And because it surrenders its energy, it converts it to water. And that water is going to stick on under the lid. So when you open the lid, you'll see the water dripping out. Remember, the water that is dripping out is at 100 degrees Celsius too. It's higher temperature. Okay, so the condensation is what takes place here. And then if you steal energy from here, it'll become water at 0. If you steal energy from here, it will turn into ice. And if you steal energy from here, it can become ice at lower temperatures. Like if I take this water and put it in the freezer, what's going to happen is this is at 24 degrees, which is here. From 24 degrees, it actually cools down to become 0 degrees Celsius water. And then from 0 degrees Celsius water, the transformation from liquid to solid takes place. And during this transformation, the temperature stays the same. Because when this starts freezing, this won't freeze altogether. It freezes on the top, and you can see, like, you can break that layer of ice, right? So it will be ice and water mixture, which is at 0. Until the entire water is converted to ice, its temperature will stay the 0. What happens after that? It can actually get super cooled, and it can actually go to minus 20, minus 40. You can actually bring it down lower. The ice cubes that you're getting from your freezer, from the ice maker, they are not at 0. They are minus temperatures. That's why they are kind of biting cold. You know, they kind of stick to your skin and all that.
Stick to your tongue.
Yes, they stick to your tongue. I mean, because it's at a very low temperature, so it kind of creates a bond. It can create frostbite. So places where the temperature is very low creates a lot of problems because of this issue. Is that clear?
Yeah.
Now, one thing you have to notice here is I'm using the equation Q equal to ml for this phase change, and I'm using Q equal to ml for this phase change. The mass is the same, but L's are different. So this is called latent heat of fusion, and this is called latent heat of vaporization. There are two different values. So what is specific latent heat of fusion? It is the amount of energy needed to change the state of 1 kilogram of a solid to liquid at its melting point. Is that clear? What is specific latent heat of vaporization? It is the amount of energy needed to change the phase of 1 kilogram of a liquid at its boiling point to a gas at the same temperature. So that is latent heat of vaporization. Numerically, the value, now which one do you think is more energy? LF or LV? Just common
LV.
logic. LV is more. The reason is, here, the latent heat is because it's gaining potential energy, but not too much potential energy, because the atoms are bonded, and what is happening between here and here is it just breaks those bonds, but the atoms are still next to each other. The atoms are still next to each other, and that requires not much of an energy. But over here, when it goes from water to steam, it is moving from the liquid out of the liquid, which requires a lot of energy. And that is why specific latent heat of vaporization is different from specific latent heat of fusion. Do you understand this part? Numerically, the specific latent heat of fusion for water, for ice water, LF is 336,000 joule per kilogram. That is the numerical value for specific latent heat of fusion for ice water. Now this is only for ice water. I'm not writing down for all substances. And whereas LV, if water is converted to steam, it is 2,250. Now you can see the difference. Right? This one is a big value, and whereas this one is a small value. Comparatively, it is small. So the amount of energy needed to change 1 kilogram of ice to 1 kilogram of water is only this much. Whereas the amount of energy needed to change 1 kilogram of water at boiling point to 1 kilogram of steam is enormous. That is why I said steam at 100 will burn you more, because it will surrender all this energy in order to become a liquid. Do you get it? Questions? Jack? Have you copied this down?
No.
Yes. All right, so this is pretty much what I expect you to kind of learn in this chapter. I'm not doing every bit of this chapter. The other thing you should understand is this. When energy is supplied to any object, the object will, it has to show that it has received the energy. I'm giving an example straight away. If I take a nail, put it on the wall, take a hammer, and just go bang, bang, bang on the nail. After hitting it a couple of times, if I touch the nail, what can you expect?
It's hot.
It's hot, right? Where did that heat energy come from? It's because of the work that I did. So you can do work on something and create heat energy. So heat energy can be a consequence of the transfer of energy. You get it? So if I put in 1,000 joules of energy while doing that job, will the nail's internal energy go up by 1,000 joules?
No.
Why? Why is the nail not getting all the 1,000?
Because it's going into the wall. You're hitting it.
Yeah, a wall also, like, wall and nail together. What about the hammer? If you feel the hammer, is it hot?
Yeah.
So the hammer is also sharing it. So all the energy is not going to one object. It is actually being shared. Is that clear?
By all three? The wall, the
Yeah, everything. Basically, it's accountable. That's all. This marker, if I'm going to release this marker from here, what kind of energy does this marker have here? Gravitational potential energy. Good. So when I release this marker, what's going to happen? What kind of energy is it getting transformed to? Kinetic energy. So after it changes to kinetic energy, now what happened? All the kinetic energy is gone. To where? To where?
Yeah.
Where is the energy gone to? Like, this had potential energy, and before hitting the table, it had kinetic energy. Now what happened to that energy? Where is it? Yes, a little bit of sound. What else? Heat on the table and on the marker. So basically the marker's temperature will go up. The marker's temperature will go up, the table's temperature also will go up. And where is that energy source coming from? From the potential energy. That's where it started off from, right? It started from here, went down, and then gets converted to the heat on the table and the heat on the marker and the sound energy, as he said. So energy is not lost. It is just being pushed here and there, and one form of energy that it can transform to is thermal energy, heat energy. So if I say half of this energy is going to the marker, you can actually use that as Q and then use the equation mc delta T and find out how much is the delta T of this marker. Because the marker has a specific capacity, the marker has a mass, so you can figure out the delta T by just knowing the amount of energy. Is that clear? Use the equation Q equal to mc delta T. So if I know that Q is 100 joules, and if I tell you the marker has got a mass of 0.1 kilograms, and if I tell you the specific capacity of the marker is 200, then you can figure out the delta T. All you do is just plug it in and get the answer. So 100 is equal to 20 times delta T. So delta T is equal to 5 degrees Celsius. So when the marker hit the table, the temperature of the marker should go up by 5 degrees Celsius. Now this is a little exaggerating. That's because this is not 100 joules. Like going from here to here is never 100 joules. It's smaller. All right? So keep that in mind. And now we are moving on to, so there is a homework assignment which is second one, homework 2. Some of you have not done even homework 1. I don't know why you are holding on to it. When you see zeros on your power score, just go ahead and fix it. Now, homework 2 is something that is due, and you should be able to complete it. Yes?
You haven't even assigned us homework one.
It was assigned.
You never told us.
I told you in class.
No, you never told us.
You never told us.
You just now told us homework too. You never told us homework.
And it was written down there as well. So anyway, it's fine. That's why I have pushed it all the way from long back to a lot of dates. Today, homework 2 must be done. And that is a homework that will be, I can push that one further. All right, moving on to the next chapter. Next chapter is chapter 10, which I'm skipping because it is thermodynamics, which is a little more extension of what you just learned. And we are moving on to chapter 11. So start with chapter 11. Take notes. Vibrations and waves. Now, a couple of these things you already know. You already know many of these things, so it should not be a tough thing at all.
Chapter 16.
Oh, did I say 16?
Yeah.
Chapter 11. I don't know why it's chapter 16. Chapter 11. Vibrations and waves. So vibrations and oscillations and all that. The first thing you should understand in vibrations and waves is a couple of terms such as simple harmonic motion. Simple harmonic motion. The word simple simply means not complex, not complicated, simple, like in simple pendulum, right? When something is moving in a very simple pattern, simple oscillation, simple. What's the word harmonic? What does it mean, harmonic?
It's like the instrument.
Harmonica. All right. What is harmonic?
No, it's like
When they're in sync.
it's
In unison.
Yeah.
There are multiple terms that you can actually like come up with. What is harmonic? In harmony. What does it mean?
They're like together.
Together. Anything else? The main meaning. In sync. What else? Any other word that can actually like support the word harmonic? Mean harmonic. You said unison, in sync, together, connected, probably. Harmony, in harmony. What is that harmonic? The word harmonic simply means rhythmic.
Unison.
In unison, rhythmic. That's the most important thing. It's got a rhythm. It's got a timing. Anything that has a timing is harmonious to your ears, right? anything that has a timing is music. Music is harmony. So basically, anything that has got a rhythm and a timing is definitely musical. Like if I just beat here like this, that's musical. You can almost feel like, you know, the beat is going to start off, and I can add more beats. Like if I just keep on doing this. And then bang, bang, bang somewhere else, and that's it. So it creates a music. All you need is that initial rhythm. Anybody knows the name of that rhythm? Initial rhythm, like the, what is that called? Metronome. Right? The metronome is the metronome. Now, what is the opposite of music?
Disarray. Drake.
Opposite of music is defined as noise. Yeah, noise.
Like
If-
random noise?
Random, like,
Yeah, that's not music.
I like that.
yeah, this is called noise. Because there is no order whatsoever. So if there's no order or pattern or nothing is rhythmic, then you define it as noise. In fact, some of the music these days is pure noise.
Oh.
Yeah,
Shots fired.
really. Some of the music is actually, I'm wondering, why is it called music? Because it's just throwing stuff into it, and there is no order or something like that you can really, you know, it's not melodious. The melody is gone now. They're just throwing a lot of stuff. That's it. So, harmonic means having a timing, having a rhythm, motion. And because it's got a timing, we have to define some of these things. That is time period. What is the definition of time period? It is a time taken for one complete oscillation. That's called time period. Time taken for one complete oscillation. That's called time period. Right, Connor? Time taken for one complete oscillation is time period. And then we have another term called frequency. And what is frequency defined as? It is a number of oscillations per second. Number of oscillations completed per second. That is called frequency. Capital T stands for time period, which is time taken for one complete oscillation or vibration. Frequency is a number of vibrations, or number of oscillations, or number of happenings per second. Is that clear? So this simply means it takes t seconds to complete one oscillation. It takes t seconds to complete one oscillation. So if it takes t seconds to complete one oscillation, in 1 second, how many oscillations can it complete? If it takes t seconds to complete one oscillation, in 1 second, how many oscillations can be completed? Yeah.
1 divided by t.
Very good. 1 divided by t. I don't know, for some reason, many students struggle with this. But if I tell you the same thing in terms of dollars and all that, you get it very easily. Here it is. $5, you get 1 cake. $1, how many cakes? 1/5. See, 1 divided by 5. You got it. It's the same thing. Instead of t, I called it 5. Instead of seconds, I called it dollars, which are more favorable to you for your brain to interpret. So, t seconds, one oscillation. 1 second, how many oscillations are completed? 1 over t oscillations completed. And the number of oscillations completed in 1 second is defined as what? Frequency. So this is frequency. So 1 over t is frequency. So frequency is 1 over capital T. And the same applies the other way. So here are some of the important equations. Frequency is 1 over time period, and time period is 1 over frequency. So basically, one is the reciprocal of the other. One is the reciprocal of the other. Now, time taken for one oscillation, what is it measured in? What's the SI unit for time period?
Seconds.
Seconds. Seconds. Now, if time period is measured in seconds, what's frequency? Frequency will be 1 over. So frequency is 1 over seconds. If that is seconds, this is 1 over seconds. And the shortcut unit for frequency is? Anybody knows it? What's the frequency of your computer?
Hertz.
Hertz. Like your processor speed, what's the frequency of its operation? If you say 2.75 gigahertz,
Yeah.
right? So using that term already, gigahertz. Giga means 10 power 9. So which means 2.75 times 10 power 9 processes can be done in 1. Right? So the unit of frequency is hertz. The unit of time is seconds. SI unit. What's the frequency of your car engine when you're driving normally? RPM. How many RPMs? Like 3000 RPM is common. If you're driving at 60, 70 miles per hour, you can actually expect an RPM of roughly 3000 to be there. Now, RPM is not the SI unit of frequency. What's the SI unit of frequency? This is revolutions per 60 seconds. So what is the frequency then? If it is 3000 revolutions in 60 seconds, 3000 divided by 60, 50. So your car engine is spinning 50 times per second. That's what it means. The car engine is spinning 50 times per second, and that's 50 hertz.
It's pretty fast.
It's pretty fast. Spinning very fast.
How fast does your car go?
This is the RPM. It depends on how you're driving. Depends on how you drive. If you're actually like idling your car, it will be like 1000 or something like that. If you're actually raising it up on a upward incline, you'll have to push it high, and so it goes 5,000, 6,000. There's always a red mark, which is a dangerous mark for RPM. So if someone is actually deliberately driving on the red side, the engine is actually reaching its, you're almost like wearing out the engine. It's going too fast for it to handle. Every material has got handling capacity. It cannot take it too much. Like for example, if I'm flying an airplane at a speed of 350 knots, it's flying really fast. At that time, if I just bring down the flaps, it can damage the flaps. Simply damage the flaps. Flaps will be gone. I mean, like it will really create problems. It can even snip off some of the wing as well. So that's dangerous. So the flaps need to be used only at certain speeds. So before they come down to land, when they reach the speed of something like 200, 220 or something like that, then they'll put a tiny bit of flap. And then after that, they'll keep increasing the flaps according to the speed and the height. So when they are landing, then they'll bring it down a lot because they're landing at only 150 or 160 or something.
They measure knots.
It's very close to miles per hour. It's like 1.1. No, the word knots is an old type of unit that they are still hanging on.
Why they go behind the...
Yeah, they still use SI units and all that. But all right, so you got the idea of time period and frequency now. Couple of things you are still aware of in terms of vibration. The The first kind of vibration is this, that you are very familiar. If a mass is connected to the spring, and the spring has a force constant of K, the spring has a force constant of K. You know what a force constant is?
Yeah.
Okay. Then this mass is going to bob up and down with the time period, which is given by the equation 2 pi radical m over k. Write it down. This is the time period equation for a spring, or for a mass bobbing up and down at the end of a spring. And this is something that you've done as a lab. And what is the idea of k? K is F is equal to kx, which means if you apply a force F on a spring, it will stretch by an extension of x. So K is F over x. The unit of K is Newton per meter, and these are things that you're already aware of, so I don't have to elaborate. So look at this equation. The more massive the mass is, what do you know about the timing? It'll be higher. What about the spring? If the spring is tough, which means high K, what will happen to the time? So the time will be like shorter. And the other thing is this. Have you done that experiment? So that's a simple pendulum. When the simple pendulum is set up, and if you oscillate it, it has a time period given by the formula 2 pi radical L over G. So time period of a simple pendulum is given by the equation 2 pi radical L over G. What is L? Length of what? String?
No, to the center, to the middle.
To the center. So the length of the pendulum is to the center of gravity of that mass. So that is the length. So the longer the length, the more the time you can expect. And G is the acceleration due to gravity, so that is an important factor as well. So a pendulum will oscillate differently on the moon, whereas a spring will not make any change. So this thing, the timing is not affected by gravity. So if I oscillate a spring like that in a space station, it will still keep the same time. So the timing is affected only by gravity for a simple pendulum. The length of the simple pendulum is what changes the time. Is that clear? Now, seconds. Look at the time, seconds. If I want a pendulum to have exactly 1 second time period, like this, the moment it moves, like exactly in sync with the seconds, what should be the length of the pendulum?
60.
Length. So to find the length of the pendulum, I want the time period of 1 second. So what do? You are going to calculate it. But before you calculate the L, since the L is under radical, the best thing to do is to get rid of the radical sign. So how do you get rid of the radical sign? Square both sides. So when you square both sides, we get this equation. And then you can plug in numbers. Now if I plug in numbers, what is T is 1 second. So 1 square, sit down. 1 square is equal to 4 pi square L over 9.8. Now what do you do to find L? Yeah, in other words, cross multiply. The best thing to do is cross multiplication. So when you do cross multiplication, what do you get? 4 pi square times L is 9.8. So what is the length? Length is 9.8 divided by 4 pi square, plug it in. 9.8 divided by 9.8 divided by 4 pi square. This is I'm showing you how to find out the length.
Like 24.
9.8 divided by 4 pi square. 0.248. You didn't put parentheses maybe. That's right.
Oh, yeah.
Yeah. So 0.248 meters, which means what? 24.8 centimeters. So the approximately 24.8 centimeters is almost like that much. Okay? So if I oscillate this, you'll see it is going with the second swatch. See? Yeah. Almost.
It's pretty close.
Very close. That's because I just took it randomly. But that's exactly how you calculate stuff when you have the time period and all those things.
Camera on?
Now the homework assignment